Whitworth quick return mechanism. Okay, this is very similar mechanism like single slider crank chain. Okay, so only the slight modification in the links. Okay, so this is very clearly illustrate what is our mechanism we are studying. That's mean the Whitworth quick return. So okay, it's like that. This is the you see, this is the fixed that's a crank shaft. You know, this is the crank. Normally this connecting rod is connected with this crank right at the end of the crank for the single the slider crank. But for the Whitworth quick mechanism, we add the additional link here. Okay, that is called slaughter bar. Okay, this slaughter bar here. So there is a one moving joint here. Okay, this joint will move along this slot. Okay, while this crank is rotated. This is the fixed frame. Okay, this is the fixed frame. So this slotted bar is fixed with this fixed frame. Okay, so at the another end of this slotted bar, we join the connecting rod. Okay, we join the connecting rod. This one is whether it's a piston or whatever is a tool you can fix. You can imagine this is a piston like a single slider crank chain. Okay, but why they put here tool? Because this specialized mechanism is used for the cutting machine. Okay, this specialized mechanism is used in the cutting machine. So instead of, you know, normally the single slider crank, crank mechanism, at the end there's a piston, right? Normally, you know, that mechanism is used in the engine, the piston and cylinder. Okay, the crankshaft and the piston. But this Whitworth quick return mechanism is mainly used in the cutting sorry cutting mechanism. Okay, that's why instead of piston they use the cutting tool here. Okay, so this is very clearly illustrate what's the difference between the single crank chain and this Whitworth quick return mechanism. You see how it's moving? This is the crank. The green one is the crank and the blue one is the slotted shaft. You see this another end of the crank when you move forward, the tool is moving slowly, but when you come back, it's quickly return. Okay, this is what the specialized the motion mechanism of this Whitworth quick return. That's why we call quick return mechanism. Okay, Whitworth quick return. So we are going to study about the kinematic diagram. Okay, the kinematic diagrams. Okay, so on the right side, okay, on the right side, everyone see there is a small, you know, my mouse hover over here, you see, right? There's a pink circles, two pink circles, and so this side they put, you see, this is the cutting tool. Okay, when you move the cutting tool in the right direction, it's we normally call the cutting stroke. Then when you when the cutting tool moving in the left direction, we call the return stroke. Okay, so this is that connecting rod. Okay, this is the connecting rod, and this one is the slotted link. Okay, then this center C, you see the center is C. This is a driving crank. This is the crank. Okay, this is the crank link. This one is a slotted. The gray one is a slotted ring, and this one is the connecting rod. Okay, so this at the end of the crank, there is a piston is moving along the slot. Okay, so you know this C is fixed. Okay, the C is fixed, and also there's the slotted link also is fixed with D, point D. Here you see my red pointer is show D and C. These 2 points are fixed. Here I mentioned this is the C center. Okay, on the right side of the on the left side of the figure you see this one is a C, is a similar this C, and this O is a fixed D. Okay, here is a they put D, but here they put O. This one is a this point D. Okay, so when the crank is rotate at the constant velocity, this at the end of the crank supposed to have a path like this. No, there's a no way. Even though this piston is moved along this slotted bar, it should move in a circle because another end is fixed and it rotates at the constant velocity, angular velocity. Okay, so it should be this path, it should be like this. Okay, and also this point is fixed, right? This point is fixed. Okay, like here D is fixed. So the D at this end supposed to rotate along this small circle. There's no way to other path. Why? Because this one fixed. The point O is fixed. So this the point A should have a path around this small circle. Okay, so in the meantime, this piston will move along this slot, but no matter how it's move along the slot, this P and this A should have always in the respective circle. So this is the special so because of this special motion, the special path, this piston also moving respective with this motion. Okay, we study in the single slider, we study single crank, the velocity is moving like this, right? Like this. This is a single slider crank. For Whitworth quick return, what going to happen is, for a forward going to take more time and return is going to be very quick. This is the return. This is the forward. Because of this special arrangement of link, this piston, this piston going to move like this. There's no equal time taken for the forward and reverse motion. For a forward going to take the more motion, for a reverse going to be less. That's why we using this specialized mechanism, Whitworth quick return mechanism. This mechanism is mainly used in the cutting tool. Normally when you cut the metal or something, it's going to take the more time. Then after cutting, it's come back to the original position quickly. Okay, it come back to the original position quickly. Then again, it cuts slowly because you need some moderate speed to cut. No, you cannot speedily, you can fast cut to the metal. So for a forward, it takes long time, and for return, it quickly come back. Okay, this is our apparatus. This is a similar apparatus with a slight different. Okay, so we are going to I'm going to explain about the main components of this apparatus. Okay,
This is our apparatus for our practical. Okay, so now I am going to explain all the components, all the parts of our apparatus. Okay, before we get into doing the practical, we supposed to know all the components names. Okay, then it will be easy while we are doing practical. Okay, let's start. Okay, this is, you know, this orange color, this one is called crank. Okay, this one you already know when we were doing the practical of slider crank mechanism, right? So this is called crank. This one is called, the long blue color rod is called connecting rod. Okay, this is one connecting rod, this one is a crank. But the additional this arm is called what? Slotted river. Okay, this slotted river is the different from the slider crank mechanism. Okay, this one is an additional arm that fixed on this mechanism. That's why we call this mechanism is a Whitworth quick return. Okay, so this is the slotted lever, this is the crank, this one is the connecting rod. You know, the below this the cube, like this one is the piston. Okay, this one is piston. Okay, this one piston, and there are two scales here. You see, this one is a linear scale to measure the piston displacement, and another scale is circular scale to measure the crank position. Understand? So what else I can show you? Okay, this one is the piston guide. You know, there is a there's an iron rod here, the steel rod. So this one is the piston guide. Okay, so you see the piston is moving along the guide. Okay, while crank is rotating, you see the piston is moving in linear motion. Okay, so these are the main components of our practical. Okay,
normally the real life, you know, you can see the cutting tool or something they have, but for our practical, instead of putting the cutting tool, we push this piston like a single slider crank chain we put. So likewise we have this block, this metal block. So we are going to study about the motion of this piston. Okay, normally I call piston. Okay, this one. So we are going to study motion of this one. Okay, how the motion of this piston. Okay, so that is our practical aim. Our practical objective is what? Investigate the Whitworth quick return. So what we are going to investigate is, we are going to study the motion of this piston. Okay, so this one is the additional slot, the red one. Okay, the red one is the, this one is the additional slot. So this one is the, you know, the brass, this steel block is the end of the crank they fixed. So while the crank is rotating, okay, this brass link, this brass metal will move along this slot while it's rotating. Okay, while it's rotating, this brass will move along the slot as well. Clear? So this is the our practical apparatus.
okay. Now we moving into the procedure part. Okay, okay. We take our lap sheet. You know, on a lap sheet, the procedure. What is the first steps we have to do on the procedure part? You know, they say set the drive crank to 0 on a circular scale. Okay, so this is the crank. This is a circular scale. Okay, so we have to set this crank to 0 degree. Okay, now we set ready. Okay, the crank position is, you see here, the 0 degree of rotation. Okay, so in the 0 degree of the rotation, what is the piston displacement? You know, on the linear scale we have to read, right? We have to read the what is the piston displacement. It's about, it's how much? You see, 10, 13 millimeter. So we have to note down this one. For a 0 degree of rotation of crank, the piston displacement is 13 millimeter. Then what we have to do? Then for every 10 degree of crank rotation, note the slider displacement. Okay. Now we have to repeat this procedure for a 10 degree of rotation. We just move the crank to the 10 degree of rotation and take the reading of the piston displacement. Here see how much? Here 11 millimeter. So for a 10 degree of rotation, how much? 11 millimeter. Likewise, we have to repeat this procedure for every 10 degree of rotation. Like 20 degree of rotation, how much the piston displacement, and 30 degree of rotation, how much is the piston displacement. So likewise, we have to do the rotation of until 360 degree. Okay, this is how we get the readings of the piston displacement versus crank rotation.
Zero angle displacement. Okay, for a zero angle displacement is 3 and 10 degree 1.5, 1.75 for 20 degree, 30 degree 0.25, 0.25, and 40 degree 0.25, Okay, we move to the result part. Okay, now we move to results part. First, what you have to do is plot a graph of a displacement versus crank angle. Okay, you just draw the graph displacement versus crank angle. Displacement on the y-axis, crank angle at on the x-axis. Okay, so you have to draw the graph. Okay, this is your first task. Second, the outer limit of slider travel across the outer limit of the slider travel occur at the crank angle of dash. That's you have to find out from the graph. Okay, you will get the graph. On the graph, you will see when the outer limit, the most outer limit will occur. Okay, at what crank angle. So after drawing the graph only, you can find out that one. Okay, from the graph you will see. For example, what do you mean by the outer limit of the slider? Outer limit mean this is the outer limit. Okay, no, maximum, the outer limit, the maximum distance maybe at the P will occur. Okay, normally this P1 and P2, okay, this P1 and P2, this distance, this traveling is for the return traveling. This one is the forward. Okay, when you run like this one is the from P1 to P2. From P1 to P1 is the forward motion of the cutting tool. Forward motion of the slider. Then P2 to this P1 is a return. You see, the P2 to P1 is a shorter than this P1 to P2, right? Clear? So you have to find out what is the degree of the crank angle, this angle, to obtain the maximum outer slider. Clear? Normally it will occur here or here. Depends on the direction of the rotation. Clear? You see, when you move like this, go down, so that time this slider will move along this slot, right? And keep this distance same throughout the path. So when you come here, the maximum distance will occur. You have to find out what is the degree of the crank position to get the outer limit. Okay, that is your second question. You have to find out from the graph. Second is the inner limit of the slider travel occurs at crank angle of that one. That is the another P1 they asking. One is the P2, another one is the P1. Okay, outer limit and inner limit of the slider travel occur at the crank angle of which angle. So that one you have to find out from the graph. Okay, after that, what is the percentage of the crank revolution when you return stroke occur? Okay, you know the full revolution is a 360. Okay, let's go back to the when you go to the question number 4, the percentage of the crank revolution when return stroke occur. Okay, so this is a return angle, right? This is a return, and this is the cutting stroke. This is a return torque. This upper is cutting, below is return. So they asking the percentage of this return angle. That's mean 360 above. What is the angle of this one? If you say theta, then theta into 100. So you know what is the percentage of the return angle. Okay, this is for question number 4. Fifth question is, what is the percentage of a crank revolution when cutting stroke is occur? Cutting stroke, as I mentioned, what? The above, right? Normally the 360 minus theta. But this reading is doesn't start with 0, right? If you notice your reading observation values, okay? So it may be start somewhere like this. So you have to find out what is exactly the cutting stroke is started and cutting stroke is finished. Okay, that is it's not a directly, you know, if you notice your observation readings, The zero, it's not start from the zero. When you put the zero angle, crank angle, you got the some displacement. Understand that? So through the graph may be like this, somehow like this. So you have to find out what is exactly the cutting stock started and what is the finishes. Understand that? But always the return stock is shorter than the cutting stock.